So there are neutron rays. Neutron rays are made from nuclear reactions that emit neutrons. Mm-hmm. My what? Oops, thank you. No, it wasn't on purpose. I don't want to waste any water.
Anything else with a little bit of industrial?
Were there any other questions? Yes, I don't know an answer to that. It's a good one. So I'll look into it. Nothing else? All right, well, I want to continue with this one, number 65. This is the one we left off with, I think. Is that correct? Yeah. So this was burned in a bomb. And we have it's already determined. So from the bomb, we have how many joules? In here, we'll put in some grams in here. And so this is joules of heat, and this is the amount. And then from that, we're going to get delta U. Delta U is going to be equal to Q over the amount. This is Q sub V. We're doing it in the bomb. And when we do that, we get minus 33.41 kilojoules per gram. What we're going to do is we're going to change the units from kilojoules per gram to kilojoules per mole. Did I calculate the molar mass for propanol? 60.11 grams per mole. Did we already do this calculation?
Yeah.
Okay, and then how many kilojoules per mole did we get?
Negative 2008.
Negative 2008 kilojoules per mole.
Mm-hmm.
Okay. You should have 4 sig figs. Give me one more digit for this. 2008.
That's all I had written down. I can recalculate that.
We'll just go with that.
2008.2751.
All right, well, let's do 0.2. Since we're not allowed that many. So we're not allowed. All right, so this is our delta U in the bomb. So we have CH3CHOH, CH3 plus. How many O2s do we have?
9/2.
9/2 O2 gas. It's going to produce 3 CO2s and 3, 6, 8 full waters.
Mm-hmm.
So we have here delta U is equal to Q plus W. Since this was done in a bomb, this is going to equal QV. Because at constant volume, we aren't going to have any work done. So this is 0. Which gives us negative 2008.2 kilojoules per mole. In this case, Q can be written in terms of an intensive. This would be intensive kilojoules per mole, or extensive. Or we would take the Q here, the QV, and divide it by the amount of reaction. Right? And so they didn't make a bunch of different equations for this. Otherwise, we'd have too many equations. And so we kind of use this interchangeably. Now, the situation is normally when we burn isopropyl alcohol, we don't do it in the bomb. Normally we do this in the lab. In the lab, it's going to be constant pressure. So what we want CH3, CHOH, CH3 plus 9 halves O2 gas goes to 3 CO2 plus 4 H2O liquids. We want to know what delta H is. If we do this, will delta H be the same as delta U? No. And how do you know? Because there's a volume change. And then the thing is, who did the work in this case? Who blew up the balloon? Did the system blow up the balloon? This is the system. Or did the surroundings blow up the balloon?
System was isopropyl, right?
The reaction. The system is a reaction.
It's going from higher to lower, so the system, the surroundings.
Yeah, right. The surroundings do. So actually, what we're going to see is delta H is going to be larger in magnitude than delta U. In other words, if we burn this under constant pressure conditions, we're going to get more heat than if we burn it under constant volume conditions. So in other words, this is going to be a larger magnitude. So I need to readjust my scale here and make that a little bit more. Now, what we want to know is how much more heat are we going to get from this? And so as we recall that delta H is equal to delta U minus what? Work. This is P delta V work, so that's equal to delta U minus P delta V. Now the delta V is going to be of the system or of the surroundings? The delta V is going to be of the system. The sign is going to correct everything for us. And so what we need to know what the pressure is. We looked at the pressure is going to be 1 bar. Did we look it up before, I think?
Oh, yeah.
On that chart, it's 1 atmosphere. We have to interchange between bar and atmosphere depending on which chart we're looking at. So that chart's in atmospheres. The chart in our book is in bar. So we're going to go with bar.
Does it matter what we choose? Because as long as the answers we clarify what units it's in.
Yeah, it will change the work a little bit because the conversion factor that we have for work is 101.3 joules per liter atmosphere. And so if we're doing it against a bar is a little bit lower pressure and it's going to be a little bit less work for the same amount of volume change. So, but it's a very small difference because the difference between a bar and an atmosphere is only like 1%. And so a lot of people ignore it because it's just a 1% error. It's a liquid at 1% error. But we'll just do it. Right. We'll see in the calculation because we have to convert it. All right. So what was the volume change? Now depends on how precise we want to be. We can ignore the liquids because the liquids are going to be roughly the same. But since we have the internet here, we can just go ahead and do this. Let's figure out the volume of 1 mole of liquid propanol. And so I'm going to just go up here. I'm going to use Wikipedia for this. And so this will be isopropyl alcohol. So we got isopropyl alcohol. And then I want to go to Wikipedia here. Actually, I don't need to go to Wikipedia. It's here. Save myself one mistake. So 1 mole weighs 60.1. If we calculate. I want one more digit here. 60.11. grams. And the density is 0.786. So if I want the volume here, the volume is going to equal, okay, 1 mole of isopropyl times 60.11 grams per mole. I'll just do it condensed here. Times 1 milliliter per 0.786 grams. 1 milliliter per 0.786 grams. And then we're going to do this in liters. Times 1 liter per 1,000 milliliters. And so what does this come out to? Now, when you guys do calculation, the problem I'm seeing is people aren't writing the units. On that last exam, I couldn't believe how many people didn't write any units. You're never going to be able to solve anything complicated without writing units. You got to get that, you got to get in the habit of writing the units. Because as the calculations can become more and more difficult, then you're going to be less and less capable of being able to do those calculations. I mean, even this isn't writing enough. I usually write more. But this is all isopropyl. We're not changing to anything else. So 60.11 divided by 0.786 divided by 1,000.
0.07647.
Yeah, okay, thank you. 0.076. Now we're allowed 3 sig figs, 6.4 liters of isopropyl alcohol. Now, we have to calculate the volume of the gas. I have the volume of the gas memorized, the molar volume of the gas memorized to 3 sig figs for 1 atmosphere and room temperature 24.45. And then for room temperature in 1 bar is 24.7, but let's go ahead and calculate the molar volume. The molar volume is RT over P. And so R is 0.08206 liters times atmosphere per mole Kelvin. T is going to be 298 Kelvin. P is going to be 1 bar. And then we're going to convert that to atmospheres. By 1 atmosphere is equivalent to 1.01325 bar. And so I get 0.08206 times 298 times 1.01325 equals
24.7.
yeah, 24.777. Is that what you have?
I got 24.
Okay, so you know what? I need to do 298.15 Kelvin. Do that. 0.08206. I want to get to 4 sig figs times 298.15 times 1.01325. 24.79 liters per mole. So 24.79 liters per mole. So I have 9 halves of moles. So that's 4.5 moles times 24.79 liters per mole at 1 bar and RT. And so how many liters will we have here? $111.5 sub 5. Actually, yeah. How much? Liters. So V initial is just combine these two volumes. So 111.55 plus 0.07647 equals 111.63 liters. This might be initial. Okay, let's go to V final. So the volume, I have 3 moles of gas here, and then the molar volume is 24.79 liters per mole. So 3 times 24.79, 74.37 liters. 0 liters of CO2. Then I have 4 moles of water. So 4 moles of water, and the molar mass of water, I have memorized, 18.02 grams per mole. The density of water, well, since we're trying to be more accurate, we get the density of water at 25 degrees C,
Should I use 999?
something like that. Density of water at 25 Celsius. $997. That should be it. Let me see if we have to enter that. Yeah, 25 degrees C. 0.9970. So we're doing 4 sig figs. So that's why I'm going to get it more precisely. So 1 milliliter is 0.9970. Sub 4 grams. So I'll throw in 1 extra digit there to minimize rounding error. And so we have 4 times 18.02 divided by 0.99704. Oops, and I need to convert this to liters. .07223 liters. So we can calculate our V final. Now take a look. What if we ignored the liquid and just focused on the gas? If I ignored the liquid, well, I had 0.076 liters here. And over here I had 0.072. Would that have led to much error? It would have led to minimal error. And so this is why the book completely ignores liquids and solids. When they do a delta V calculation, the delta V calculation only involves the gases. And that's because there's little change in the volume of the liquids. Even though, you know, it's one liquid's propanol, the other liquid's water, there's very little change. We could have done the same thing as well. You know, if you're pressed for time, you would just calculate delta V based on the gases alone. This is not going to change the answer that much. And so we end up with a V final of 74.442 liters. All right, let's figure out what our delta V is. Our delta V is V final minus V initial. V final is 74.442. V initial is
1.63 liters.
It comes up to minus 37.1 sub 8 liters. We're only allowed 1 decimal place here. according to the rules for sig figs. We're going to end up with 3 sig figs in our delta V. Okay, let's calculate the work. The work is equal to minus P delta V. So P is 1 bar, exactly. Delta V is minus 37.1 sub 8 liters. And so this is going to give us 37.818 liters here. And times bar. Now we need to use our conversion factor. Our conversion factor is 101.3 joules per liter atmosphere, not liter bar. So I'm going to change bars back to atmosphere. And so 1 atmosphere is equivalent to 1.01325 bar. So the bar cancels, the atmospheres cancel, and that leaves us with joules. So we'll go 37.18 times 101.3 divided by 1.01325. Comes out to 3,717 joules, or 3.7. So how many sig figs in all? 3.71 sub 7 kilojoules. This is positive. Now, this work is extensive, right? But it's also intensive because that's the amount of work for combusting how many moles of propanol?
1 mole.
Yeah, 1 mole. Or we could say 3.717 kilojoules per mole of propane that's combusted. Oh, actually, isopropyl. I'll just call it IP, isopropyl. All right, so we have delta U as an intensive. Delta U was minus, what was it, 2008?
Yeah.
Minus 2008 kilojoules per mole of propane, or no, propane, isopropyl. Okay, minus, okay, now this is going to be plus, a plus 3.717 kilojoules per mole of isopropyl. And so that's going to give us minus 2011.7. We're only allowed this many decimal places, so I'll drop the remaining ones. Kilojoules per mole. And we end up with minus 2012 kilojoules per mole. So how much extra heat? We get this is a little bit of extra heat. If we burn this in a bomb, we get 2008 kilojoules released. If we burn this in the open lab, we're going to get 2012 kilojoules released. So we get an additional 4 kilojoules, roughly, of heat. It's not much, but where does that 4 kilojoules come from? That 4 kilojoules comes from the surroundings. The surroundings having to blow up the balloon. Russian gases. You might have known, you might have experienced that. You know, if you have like a can of compressed gas and you squirt the compressed gas out, like, you know, those dusting, have you had those keyboard dusters? You know, the can gets really cold. The can gets really cold because it's doing work to expand the volume. And so that work being done is taking heat out of the can and heat out of the air to do the work. Or when you compress gases, it gets hot. So if you ever pump a bike tire or pump a car tire, you feel the pump, it's starting to get hot because, of that. And so we see this heat stuff happening. So anyway, this is an example of relating to this. What's much more useful is not delta U. We don't do things in a bomb usually. We do delta H, but it's just much more convenient to burn it in a bomb and then calculate what the delta H should be. And then once we have the delta H, then we can use this. So the way we use the delta H is very simple. We use it as a stoichiometric or conversion factor. So if we burn a full mole, we get that. If we burn 2 moles, we get twice as much. 3 moles, 3 times as much. Or if we burn a certain number of grams, if we burn 40 grams, we can calculate how many moles that is and then figure out how much heat that is. And so we're going to use our delta H to do energy calculations. And so delta H is going to be very useful for that. And delta H is something that we want to determine and something that we want to know. We want to know, and this delta H is called the delta H of combustion of isopropyl alcohol. And so that's going to be very useful for us. This is a combustion reaction. So we call this delta H of combustion. This is delta U of combustion over here, which we had calculated earlier. 66, write an equation to represent the combustion of thiamol referred to in exercise 44, including this equation values of delta U and delta H. So if we go back to exercise 44, this is a typical type of problem here. If you have a sample of thiamol, you want to figure out what is delta H of combustion of thiamol. Okay, so that's what we want, because then we can use delta H to predict how much energy is released in these particular reactions. So we don't have delta H. Actually, we can look it up. Delta H of thiamol. Thiamol is a common chemical. And people already know what delta H is, but let's pretend we didn't know what delta H is. If we didn't, then we take a sample, a small sample. We don't want to burn a full mole of this. It would take a long time, and it's not really necessary. So they burned a 1.397 gram sample of this. Okay, now you can burn it in a bomb or you can burn it in the open lab. Well, it's much easier to control in a bomb, for calorimetry. It's much easier to take temperature measurements for things that you burn. If you're doing a neutralization with HCl aqueous, sodium hydroxide aqueous, then we don't want to use a bomb for that. It'd be a waste, but something like this, we're going to use a bomb. So it's burned in a bomb calorimeter assembly. The temperature increases 11.23 degrees C, and the heat passes through the bomb. So somebody had to calibrate the bomb. And whoever calibrated the bomb figured out for every degree C temperature increase in the bomb, it requires 4.68 kilojoules worth of energy. And so we're doing more than 10, so this is going to require more than 10, maybe around 50 kilojoules to increase it by this temperature. So what is the heat of combustion of thiamol expressed in kilojoules per mole? And so we could do this calculation. So from the bomb, we'll figure out what delta U is. So this is number 44. Delta U is going to be the amount of heat under constant volume divided by the amount. That's what our delta U is. And so how much heat was evolved? Well, how much heat was evolved was, depending on our delta T here, was 11. This is from the calorimeter. So QV of combustion is equal to minus Q of the calorimeter. Because all the heat of combustion goes into warming up the bomb calorimeter. The calorimeter is an object. So if we have an object, then it's going to be minus the amount of calorimeter times C of the calorimeter times delta T of the calorimeter. The amount of calorimeters, we only have one calorimeter, so this can be 1 times the C of the calorimeter. What's the C of the calorimeter? That's given as 4.68 kilojoules per degree C times delta T. And delta T is already given. Temperature increased by 11.23 degrees C. And so this is going to tell us the calorimeter absorbed that, therefore the reaction, the combustion reaction must have released that. And so what does it come out to? 52.55.
52.6.
Okay. So we're going minus 52.5.
And then 5, unrounded.
Unrounded. Okay, we want unrounded. Kilojoules. Okay, this is the amount of heat for how much do we burn? Well, this is not a full mole. And so what we're going to do is we're going to convert this here into an intensive ratio. That is minus 52.5 kilojoules for the amount. What was the amount? 1.397 grams of thymol. Then we want the molar mass of thymol.
Well, that should be about 150.14.
150.1 kilo?
Yeah.
So 1 mole is 150.14 grams. Is that correct? All right, so let's go ahead and calculate this. So it's going to be 52.55 divided by 1.397 times 150.14. And so we get a delta U of minus 5,647.7. We're only allowed, what, 3 sig figs? So this is too many. Yeah, 3 sig figs. So we'll just substitute this then. Kilojoules per mole. All right, now when we burn thymol, we don't usually do it in a bomb. So what we need to do is we need to do a calculation to see if I didn't do it in a bomb, would the volume have changed? If the volume wouldn't have changed, if I didn't do it in a bomb, then delta H and delta U are the same thing. If the volume changes, then delta H and delta U are not the same. And so I'm going to try to do this one quickly. Let's see. So again, this is an exothermic reaction. So we have C10H14O solid. C10H14O solid. O solid plus O2. This is going to yield CO2 plus H2O liquid. And so I have 10 carbons, so I'll need 10 CO2s. And then I have 14 hydrogens, I'll need 7 waters. And that gives me 27 oxygens. So I'll need 26 plus 1 here, so I'll need 13 here. Okay, now look, was there a volume change?
Yes.
Yes. There was a volume change. If I went from 13 moles of O2 to 13 moles of CO2, I could ignore the solid and liquid because the volume would be negligible. So delta U and delta H are practically the same thing. But in this case, there is a volume change. Since the volume change happened, we're just going to go with this. Is this going to be in bar or atmosphere? Yeah, that's the book is in bar. All right, so we're going to just say the pressure is 1 bar. That means the molar volume is 24.79 liters per mole. So 1 bar and 25 degrees C. 25 point, 25 degrees C, exactly. So this is a useful number to remember, 24.79, because the book likes bar. If the book liked atmospheres, then 24.45 is a good number. Or just rough calculation, 25. You know, it's roughly 25. Depends on how fast you need to do the problem. If we need to do this problem quickly, that is, it's multiple choice or something, then I would just do it 25 liters. And calculate it. So the difference here is 3 moles. The distance to 3 moles is 75 liters. So it's minus 75 liters. I'm going to get an answer that's very close. Correct? But since I'm on a, maybe it's not multiple choice, maybe I need to write the actual answer. If I need to write the actual answer, then I'm going to figure it out more precisely. So our book, what our book does is, okay, this is delta H. Delta H is equal to delta U minus W. Remember, this is our net. This is our net income. Our net income is based on our gross income minus work or tax. All right, so what we're going to do is we're going to just look at delta V of the gas. And we're going to ignore the solid and liquid volume. And so delta V of the gas is, well, we have 10 minus 13 moles. And so that's minus 3 moles of gas. And we have minus 3 moles of gas, and then each mole of gas is 24.79 liters per mole. How many liters was that?
74.37.
74.37 negative liters. Okay, now let's calculate the work. Okay, so I have my delta U, which is minus 5,647 kilojoules per mole. Okay. Minus the work would be a minus P delta V. P is 1 bar exactly. And our delta V is a minus 74.37 liters. And so this is going to give us liters bar. And so I need to convert that to liters atmosphere. So 1 atmosphere is equivalent to 1.01325 bar. This gives me liters atmosphere. And then I'm going to use the one I memorized, 101.3 joules per liter atmosphere. And then I want the units to match. So this is in kilojoules. I need to make this in kilojoules too. So 1 kilojoule is equivalent to 1,000 joules. And so what does this term come out to here? So 74.37 divided by 1.01325 times 101.3 divided by 1,000. 7.43. So this is minus 5,647 kilojoules per mole minus, this is going to be minus, this is positive. So this is going to be minus 7.43, about 3.35 liters. I mean, not liters, kilojoules. Now, this is how many kilojoules for how much are we burning? Even though the units here are in kilojoules, this is kilojoules per mole. So I can just add that on here because that's how much I'm going to get when I combust 1 mole. So this is kilojoules per mole as well. And so I'm going to end up with 5,654 kilojoules per mole negative. And then I'm going to change this. I'm going to change it to 3 phase. 5.65 times 10 to the third kilojoules per mole. Negative. So if we burn this in a bomb, we get 5,600. If we burn it, well, 647. If we burn it in the open air, we get 5,654. Was there a big difference in energy? Not much, but a slight, we got a little bit more energy burning it in the open lab. In the bomb. All right, so what we want, there's certain quantities that we want to know, and these are compiled in tables. So when we're dealing with objects, what do we want to know? When we're dealing with objects, we want to know the amount, of course, and the amount's going to depend on the problem. And so the amount will change. But something that won't change will be the heat capacity. So when we're dealing with objects, we want to know the heat capacity. How do you determine the heat capacity? Well, you determine it using calorimetry experiments. We talked about calibrating the bomb. We also talked about calibrating the styrofoam cups. So we did two calculations. One calculation was calculating the heat capacity for the styrofoam cups, the probe, the lids, all that other stuff. Heat capacity of calorimeters change, but there are other heat capacities, like heat capacity of gold, heat capacity of lead, heat capacity of whatever for specific heats. So we want to know the heat capacity or specific heat for objects. For reactions and processes, we want to know delta U or delta H. Primarily it's delta H. That's the one that we want to know the most. How do we determine delta U's and delta H's? We do calorimetry experiments, right? Right, we do calorimetry experiments for both of these to determine these. And these are found in tables. Because, I don't want to repeat do you want to, each time you use this bomb, do you want to recalibrate it? Not really. Hopefully the calibration stays correct.
No weakness in that, the heat capacity goes down.
Yeah. So these are the types of things we want to do, but okay, let's take a look at some of these problems here that we have. This is typically what we do. Calorimetry. Actually, we did some of these already. This is calibrating the bomb. A sample gives off 5,228 calories when burned in a bomb calorimeter. The temperature of the calorimeter simply increases 4.39. So we know how much heat per degree C. So this gives us the heat capacity of the bomb. Each bomb is unique. So each bomb will have a different heat capacity. Do that. 36, the following substance undergoes complete combustion in a bomb calorimeter. The calorimeter assembly has a heat capacity. So somebody already did heat capacity. In each case, what is the final temperature? So here, we have how many grams of caffeine we're burning, and they tell us the heat of combustion of caffeine. So if this is the heat of combustion, then we know how much heat released per mole. And we have how many grams, so we'll go from grams to moles to kilocalories, and then figure out what the temperature increase should be. So that's a different type of calculation. 37, a bomb calorimeter experiment was performed with xylose. We did this one. Looked at that, or at least looked at that before. Here they're adding something here. What is the heat of combustion of xylose? Write the chemical equation for the complete combustion of xylose and represent the value of delta H of R in this reaction. We assume for this reaction delta U and delta H are about the same. They're assuming it's about the same because the moles of gas didn't change. I think the moles of O2 and moles of CO2 are the same. The only difference was the solid and the liquid water. And the volume changed to minimal, so that's why they're saying delta U is approximately equal to delta H. You recall this one? Okay, a coffee cup counter, remember this constant pressure, and so we're going to get delta H from this. Bottom, we get delta U. Coffee cup calorimeter contains 100 milliliters of this, and then you add some zinc to that. And so the HCl reacts with the zinc. So this is the reaction here. It's a single replacement reaction. And so, what is the heat of reaction for mole of zinc? Make the same assumptions as in example 7-4 and also assume that there's no heat lost with the hydrogen that escaped. So did they give us the heat capacity of the calorimeter here? No.
Not obviously.
No, they didn't. And so the assumption that they made was that the calorimeter was so well insulated that no heat was lost to the calorimeter. Yeah, it's just a perfect insulator. And so they're completely ignoring it. That happens sometimes, you know. If it's really well insulated, then you're going to lose very little heat, and it's going to lead to very small error. But a small error they can live with. But normally what we like is we'd like to do it without assuming that no heat is lost. I mean that there is heat lost to the calorimeter. 39, here, KCl is added to water. So this is a dissolution. So this is a process, the dissolution of KCl. It's actually endothermic because the temperature drops. And so it's got to be endothermic because it's taking heat from the surrounding. What is the heat of solution of KCl? Well, the heat of solution of KCl, again here, do they tell us the, how much heat is lost to the styrofoam cup? No, so what they're asking us to do here is assume that no heat's lost. The styrofoam cup's a perfect insulator. And so all the heat came from only the water in the cup, not the water in the cup. Does that make sense? The heat of solution of potassium acetate. Okay, so this is another one. They tell us the heat of solution here. And so this is our delta H, or delta U because there's no change in volume. So delta H and delta U are the same. What will be the final temperature when 2.241? So this is the type of problem we want to do. You know, this is how many kilojoules per mole is released. If we have not a full mole, we have a quarter mole, then we're going to get a quarter amount of heat. So it's going to be a quarter of the amount of heat. And if we get a quarter amount of heat, then where does that heat go? It goes into the surroundings. So the surroundings is going to be what's left over after you dissolve it. What's left over after you dissolve it is the solution, 815 milliliters of solution. We're assuming that when we dissolve this, it doesn't change the volume. Initially at 25.1, so that solution is going to warm up. In other words, water is going to warm up. And this is in a styrofoam cup probably, and the styrofoam cup should warm up too, but we're ignoring it because they aren't saying anything about it. A 1.620 gram sample of naphthalene is completely burned in a bomb. So this is constant volume. If you can heat of combustion with naphthalene, so they give us the heat of combustion. This must be a delta U. And so this is figuring out the heat capacity of the bomb calorimeter. So this is calibrating the bomb calorimeter. 42, salicylic acid has been suggested as a calorimetric standard. We talked about that one too. This one's calibrating the bomb. We did this one, I think, or something similar. Based on the heat of combustion of sucrose, establish what should the temperature change produce in the combustion. So they give us the heat capacity of the bomb. They just want us to predict the temperature change. Usually we don't do such calculation. Usually. The only thing is to make sure it doesn't exceed 100 degrees C. Because if it exceeds 100 degrees C, then the water is going to start to boil, which is going to change the heat capacity of the bomb. So the only reason you do this to figure out the final temperature is to make sure the bomb doesn't go over 100 and the water inside the bomb starts to boil. 44, this is the thymol we just did. 45, 5-gram sample of sodium chloride. So this is the heated solution. They tell us the heated solution. What is the mass in grams of water and styrofoam cups? You know, all the heated solution goes into warming up the water, i.e. the salt water in the cup. And so the salt water started initial here. We just got to figure out the final. 46, we can determine the purity of solid materials by using calorimetry. A gold ring for pure gold specific heat capacity is equal to 0.1291 joules per gram degree C of Kelvin. Kelvin and degree C are the same. With mass of 10.5 grams is heated to 78.3 degrees C and immersed in 50.0 grams of 23.7 degrees C water in a constant pressure calorimeter. The final temperature of the water is 31.0 degrees C. Is this a pure sample of gold? And so they tell us what the heat capacity is, but they want us to determine what the heat capacity is, what the gold is. So what we do is we look at how much the water temperature increased, and all that heat came from the hot gold. So the hot gold cools, and the water warms. They don't give us the heat capacity of the bomb. Do you see that? And so all they're saying is all that heat's going to go into the water. Really, all that heat's going to go into the water and the bomb. And so this is a little bit screwed up because they should tell us what the heat capacity of the calorimeter is. They don't. And so again, we're ignoring the calorimeter and just assuming that the hot gold transferred all its heat to the water, the cold water. The hot gold cools, the cold water warms. So this is object and object. Okay, when do we see the heat capacity of the calorimeter come in? We don't see the heat capacity of the calorimeter come in until we get to the advanced problems. When we get to the advanced problems, finally they're not going to ignore that some heat's going to be lost to the coffee cup calorimeters. So let me see if I have that. Okay. Okay. It's in here, but the calculation is going to be very similar to the calculations I did in lab for experiment 2. It's the same type of calculation. And so, since I already did the example for the lab, I'm just going to skip this example here. I was just going to mention it, that it's in there. All right, so we can use, what we want is we want delta H. Now, how many reactions are there in nature? Too many to count. You know, as objects, there aren't that many. Well, there are a lot of objects and mixtures as well. And so the heat capacity, or the specific heat of an object, we just get from the table. Somebody had to measure it. And if you have a new object, then you're going to have to measure it. But there are so many reactions that when we think about delta H, that's a lot of measurements. And so it turns out that we don't always have to do calorimetry to figure out what delta H is. And so let's talk about delta H. Delta H is going to be the most useful for us in determining how much energy we need. And so we take a look at this particular problem. This would be like a delta H problem. It would be number 108, like this. Number 108, the metabolism of glucose yields CO2 and liquid water as products. Heat released in this process is converted to useful work with about 70% efficiency. Calculate the amounts of glucose metabolized by a 58.0 kilogram person in climbing a mountain with an elevation gain of 450 meters. Assume that the work performed in the climb is about 4 times that required to simply lift 58 kilograms by 1,400 then they don't give us delta H of combustion. What we need to know what delta H of combustion is. And so let's talk about delta H. The first thing is delta H is a state function. And so it doesn't matter what the path is. And so these are some relationships with delta H. So if we have glucose, C6H12O6, and we burn it, 6O2, it's going to yield CO2 and water. And so we can burn this, that is, we can combust it. But the same thing happens in our body. If we eat solid glucose and we inhale oxygen, eventually that glucose is going to be converted into what? Well, your body's going to want to maximize all the energy it can get from this. So it's going to completely oxidize the glucose in your body to form what?
CO2 and water.
CO2 and water. And so you're going to exhale the CO2, and we're going to get energy from this process. Now, are we going to get a different amount of energy or the same amount of energy? So you would imagine less energy, but
Imagine more.
you imagine more?
Yeah.
Well, no, we're going to get this exact same. So delta H of combustion is equal to delta H of metabolism because these are state functions. We're going to get the same amount of total energy. Whether we use it efficiently or not is a different story. And so we'll get the same amount of energy, but what we do with that energy, remember this is the net. This is your usable energy here. What we do with it is we either convert it all into heat or we use some to do some work. Right? And so delta H of combustion, delta H of metabolism are the same because delta H only depends on the final minus the initial. And since the final and initial are the same here, they're the exact same. And so that's it. Now, the situation is, what is delta H of combustion? Well, we could burn this in a bomb, and then if we burned this in a bomb, was there much volume change here if we would have burnt this in the constant pressure? No. And so delta U and delta H are pretty much going to be the same thing. Do you see that? Because the delta V of the gas is 0. And so the only delta V we're dealing with is the gas, solid, and liquid, which is going to be so small, it's going to lead to a very small error. So we usually don't really care about such a small error. But do you want to do calorimetry? So how can we get delta H? Well, one, we can do calorimetry. Calorimetry is a lot of work. Bomb calorimetry and then convert it into delta H. But are there alternative ways we can do it? There are. Since it's a state function, we have this interesting thing here that delta H of the forward reaction is equal to minus delta H of the reverse reaction. So if we drop down 1,000, then we have to climb up 1,000. And so one might be negative 1,000, the other is positive 1,000. Well, that's not going to help us here. The delta H to the forward and reverse is just opposite in sign. Then 3. What else do we have? Well, it's an extensive property, right? And so, if it's per 1 mole or per 2 moles, it makes a difference. And so we got to watch out. It's an extensive. Energy is extensive. Delta H is intensive, but it's fixed per mole. And so that can change it. Like if I have 2 moles, then I just double it. So, for example, 2 moles means 2 times. And so an example of this would be, let's say I knew it was minus 5,000 kilojoules per 1 mole means it's equal to minus 10,000 kilojoules per 2 moles. Well, that's not a big revelation. But because of this, because it's an intensive property, we have something called Hess's law. Hess's law says that delta H of the net reaction is equal to the sum of the delta H's of individual steps. So the steps are going to be, if I can sum up the reaction, so for example, this would be delta H of reaction 1 plus delta H of reaction 2 plus ... And so there are two methods for this. Method A is just some random equations, seemingly random equations. That you can use. Method B uses only one type of equation. And these are formation reactions only. Formation reactions only. And so let's say I have an unknown delta H, but I have a library of other delta H's. So let's look at number 70, for example. This would be an example of 4A. Number 70. Okay, so the reaction I'm interested in is nitrogen gas plus oxygen gas yields 2 nitric oxide gas. And we want the delta H for this. This is essentially combustion of nitrogen to form nitric oxide. So what is delta H? And then I look at my library of chemical reactions and delta H's. And then I know, given these known values, So what are the known values? Here, this is 1/2 nitrogen. These are all gases, except for the last, I'll just write gas. Plus 3/2 hydrogen gas yields NH3 gas. So this is delta H1. So that's reaction 1. And this is a known value. This is the formation of 1 mole of ammonia from the elements here. The next reaction is going to be NH3 gas plus 5/4 O2 gas yields NO gas plus 3/2 H2O liquid. This is our delta H2. And the final reaction that we're given is H2 gas plus 1/2 O2 gas yields H2O liquid. All right, the way we do this is we look at each. So what do I want on the left? What I want on the left is 1 mole of N2. But when I look at these reactions, I have 1/2 mole of N2. If I have 1/2 mole of N2, it's simple fix. What do? Multiply by 2. So if I do that, I'm going to get N2, which is what I want over here. I'm looking at N2. Okay, plus 3H2. This is going to yield 2NH3. Well, if I'm making 2 moles of ammonia rather than 1 mole of ammonia, then it's going to cost twice as much energy. So this is going to be 2 times delta H1. All right, now I have 1 mole of N2. That's what I want, 1 mole of N2. The next thing I want is 1 mole of O2. But when I look at O2, I have two different equations that give me O2. So I'm going to skip that for now. I'm going to skip it and go to NO because when I look at my equations, there's only one of these equations that has
Yeah, no gas.
the NO gas. And that's this equation here. But I want 2 moles of NO, but I only have 1 mole of NO. So what do I need to do?
Multiply by 2.
Multiply by 2. So this is going to give me 2 NH3 plus, that's going to be 5 halves O2. This is going to yield 2 NO. And this is going to be plus 3 H2O. This is going to be 2 times delta H 2. And that's going to give me my 2 moles of NO. So right now I'm getting closer, N2 and 2 NOs. And then look at what happens to the NH3. Do you see what happened to the NH3? I have 2 NH3s on the left, 2 NH3s on the right. They're going to cancel. Anything else? No. Nothing else. What don't I want? You know, I don't want 3 H2Os. Right?
Right.
I don't want, how can I get rid of it? And I don't want this hydrogen and oxygen, right? Or no, I want some oxygen. I don't want that hydrogen. Well, this one will get rid of H2O. Do you see it will get rid of H2O?
Yes.
If I flip it backwards and multiply it by 3. So what I'm going to do is I'm going to flip it backwards and multiply by 3. So this is going to be 3 H2O. This is going to produce 3 H2s plus 3 halves O2. And so if I flip it backwards, that's the reverse. If I reverse it, what happens to my delta H?
It becomes a negative.
It becomes a negative, and then I multiply it by 3. So this is going to be negative 3 delta H3. And so now let's add it up. The 3 H2Os cancel, the 3 hydrogens cancel, and 3 of the 5 cancel. The 3 of the 5 cancel, that leaves me with 2, and that becomes 1. And so the net reactions N2 plus O2 yields 2NO. And delta H for this is going to equal 2 times delta H1 plus 2 times delta H2 minus 3 times delta H3. And then I just plug in the numbers there and calculate it. Okay, so I didn't have to do a calorimetry experiment for this. I could use Hess's law to determine an unknown delta H. For gases. Okay, there's an easier version of Hess's law. If I have the data. And that's 4b. This is easier if data is available. And I'm going to use delta H sub F superscript 0. The superscript 0 means standard conditions, standard thermodynamic conditions. What are standard thermodynamic conditions? Okay, it turns out it's not 25 degrees Celsius.
Is it 0 degrees Celsius?
No, no standard temperature. There is the common, what's the most common temperature? 25. What it means is the gases are at 1 atmosphere or 1 bar, and the solutions are at 1 molar concentration. And then F stands for formation. A formation reaction is the formation of, formation of 1 molar product. Of 1 mole. Not 2 moles, not half a mole, but 1 mole of product. 2, from the elements in their stable state. And that's what we call a delta H of formation. These are in Appendix D. Found in Appendix D for data. So all we do here is if we want the delta H of some reaction that we don't know, then what we do is we sum up the delta H's of formation of the products, where nu is the number of moles, because it's energy sensitive, so we need to know how many moles of each product we have. So it could be nu key, but it's nu per whatever we're looking at, minus the sum of nu times delta H of formation of the reactants. So actually this turns out to be a lot easier. So if we wanted to do N2 gas plus O2 gas yields 2NO gas, then we can solve it this way too. So delta H of this reaction under standard conditions is equal to the sum of the delta H's of formation of the products. Well, we have 2 moles of NO times delta H of formation of NO. The delta H of formation of NO we look up, minus, okay, the sum of the reactants. So we have 1 mole of N2 times the delta H of formation of N2 gas, plus 1 mole of O2 times the delta H of formation of O2 gas. It makes a difference if we form a gas or a liquid or a solid. Okay, so what we're going to do is we're going to look up the numbers in Appendix D. So I'm going to jump to page, maybe it's A15 or something. Let's go to A20. Okay, here we are. This first column is the delta H of formation under standard conditions here. And so this is by element. And so the first one we're going to look up is nitrogen. So let's go, it's alphabetical, so we're going to go to N for nitrogen. Look up nitric oxide. Here's nitric oxide. And the delta H of formation is 90.25 kilojoules per mole of nitric oxide. So we're going to get 2 times 90.25 kilojoules. The moles cancel out. All right, minus the delta H of formation of nitrogen. So when you look at the delta H of formation of nitrogen, what is it? 0. Now, why is that? Well, it's because of the definition. The formation reactions aren't written. We just have the number here. So if we're forming NO, then the reaction is we're going to take the elements, 1/2 nitrogen plus 1/2 oxygen, to make 1 mole of NO gas. This is the formation reaction. So we're forming 1 mole of product from the elements in their most stable state, gases in this case. Well, okay, let's look at the formation of nitrogen. If we look at, we're going to form 1 mole of nitrogen gas from the elements in their most stable state. What is the element, nitrogen? And what's its most stable state? N2 gas. So if we form N2 gas from N2 gas, is there any change?
No.
And so The formation of any element is zero in their most stable state. It's zero because there shouldn't be any change. Over here, the delta H of formation is not zero. The delta H of formation is 90.25.
Does this only apply in Hess's law? Does the N2 was equivalent to N2 only apply in Hess's law, or does it apply?
No, this applies for formation reactions. It doesn't have to be Hess's law. So we use these. In this particular case, all these are delta H of formation. And so this first column here is primarily for Hess's law, but sometimes it's not. You know, sometimes this is the reaction. So if we have the reaction, we can look up, you know, so I don't have to do anything. So for example, if I'm looking at the reaction, N2 plus 2H2 yields N2H4, and I want the delta H for this, then I don't have to do anything because this is the delta H for that reaction here. And so this doesn't even require Hess's law. It's already done. And so oftentimes I'll just use the numbers right off the table for this, but it's being able to recognize it. And so what do you think the delta H of formation of oxygen, O2 gas is? Zero. So this is going to be minus 0 plus 0. And so this is going to give us 180.5 kilojoules. Which is what we would have calculated if they gave us the numbers earlier. But it's a lot less work. Do you see how much less work that is?
Yes, I do see it.
Okay, now once we have the delta H, then we can do things with this. And so let's go back to this problem with the mountain climate here. Okay, let's take a look at number 108. So the metabolism of glucose in other words, we want the delta H of combustion of glucose. Glucose is C6H12O6 solid plus 6O2 gas. Is going to yield 6 CO2 gas plus 6 H2O liquids. Number 108. In other words, we want to know what delta H of oxidation is or delta H of metabolism for this is. Do they give it to us? Unfortunately, they don't give it to us. You know what they give us? They give us delta H of formation of glucose. Delta H of formation of glucose is not the same as this reaction. And it is nowhere close to the same. Delta H of formation of glucose is the formation of 1 mole of glucose. Well, 1 mole of glucose is C6H12O6 solid from the elements. Well, the element of carbon is either graphite, diamond, or whatever. And this graphite's the most stable. So it's going to be carbon, graphite. We'll need 6 of those. And the element hydrogen is going to be H2. So we'll need 6 hydrogen gases. And the element oxygen is O2. So we'll need 3 O2. And so this is the delta H of formation. Do you see it doesn't match? And so we want the delta H of this particular reaction. The delta H of this reaction, we're going to use Hess's law with formation because that's going to be the easiest. So I need the delta H of formation of 6 moles of CO2. 6 moles of CO2 times the delta H of formation of CO2 plus 6 moles of H2O times the delta H of formation of H2O. Now, it has to be H2O liquid. Solid and gas would be different. Minus the delta H of formation of glucose. So we have 1 mole of glucose times the delta H formation of glucose. It's called GLU. Plus 6 moles of O2 times the delta H formation of O2. Well, what's the delta H formation of O2?
0.
0. So this term is 0. So I have to look up the delta H formation of CO2 and the delta H formation of water. So let's do that. This is going to be I think it was A19 carbon. Okay, the delta H formation of CO2 gas is minus 393.5. So this is going to be 6 times minus 393.5 kilojoules. The moles will cancel. Plus the delta H of formation of liquid water, because it's hydrogen, A, B, C, D, E, F, G. So it's probably going to be a next page one. Hydrogen here. And so H2O liquid is delta H negative 285.8. So this is going to be 6 times negative 285.8 kilojoules. This is going to be minus the delta H of formation of glucose, which was given in the problem. And so let's go back to the problem there. And the delta H of formation of glucose, actually, this is probably in Appendix D. Glucose is such a common chemical. Minus 1273.3 kilojoules. And minus 1273.3 kilojoules per mole. We have 1 mole. So this is going to be plus. And so now we can figure out what delta H of combustion or delta H of this reaction is.
Negative 2,802.5.
Negative 2,802.5.
Yeah, 5 is a added digit.
Okay.
We have 4 significant.
Okay, that's good.
Oh wait, no, this is addition. Never mind.
Or we could say this, or negative 2,802.5 kilojoules per mole glucose. That's how much glucose we have there. So we can write this. This is for this reaction as written. This is just in general. That's the way we write it. We can express it in different ways. Even though the moles canceled out, we know what the moles are. And energy is extensive, so it really depends on the amount. Unfortunately, we're out of time. I wanted to finish this particular problem, but we don't have enough time to finish it. Yeah, so got to figure out how much glucose. I'll stop.